start a different one. Okay. Now, what I want to do is something I believe every maths teacher should know, but for some reason they don't. So this bit's a bit difficult to swallow because there's a lot of algebra in there. So what I'm going to do is take the general form and I'm going to complete the square, just like we did before, with some housekeeping. Okay, so the first step I'm going to do is divide through by A, and 0 over A is still 0, and we can see that they cancel, and so we're left with x squared plus b on A plus c on A. Okay, the next thing I'm going to do is complete the square, because I've put it into the correct monic form. And I'm going to take the coefficient of plus b on A, and I'm going to halve it. Then I'm going to take that and square it. Now, using the rules that we know exist, we can split those off. Now please notice this. What happens with the indices here? 2A has inside there hidden indices. Okay, 1 and 1. What do we do with the indices and the outside the bracket? What's the rule? Yeah, we times them. Is that what you said? Okay, so we equal. So it's 1 times 2 and 1 times 2. So it's 4A squared. Now, I want to say to you, many students that we get at university, if I give them a quiz on that, they won't pass it. Some algebraic skill there. It's a real weakness in some of them. Alright, so that there is our square. That goes together with our two terms. Plus, I'm going to add it to both sides or balance the equation. Here's my shifter. If I add b squared, I should subtract it. Doesn't look like it's ready to be made into a perfect square, so what I'm going to do is clear fractions. How do you clear fractions? Multiply by highest denominator. Common multiple. Okay, so in this one here, the highest common multiple on the denominator is 4a squared, so I'm going to times by 4a squared to clear fractions. Okay, so everything gets a 4a squared multiple. Me being the long way teacher. And of course 0 times 4a squared is just 0. Alright, so then we can go through and do a few knockouts. So we can cancel the 4a squares. You should put 1s there, that's reasonable. 1 and that becomes a 1. 4a squared there becomes a 1, that becomes a 1. And we've got an a that will cancel, that'll become a 1. So all nice and nifty, I get 4a squared x squared plus 4abx plus b squared, that's our perfect square, plus leave a gap, 4ac minus b squared. Okay, so that's looking good. So this is now a perfect square in what? It's a perfect square. What goes in here? There's all pluses, so it's going to be a plus. Well, I'm going to cheat because the last term is b, so that's going to be a b. So b times b is b squared, tick. What have I got to put in here to get these? So I've got to put something in here. It's this something times b times 2. So let's try something times b times 2. So I've already got a b. So it's ax, and it looks like 2ax. Let's try that.
2ax.
So 2ax squared, 4a squared x squared, tick. 2ax times b is 2axb times 2 is 4a. We did it, text. Okay, so we've got 4ac, so that's our perfect square, minus b squared equals 0. Okay, so we need to do a bit of undo. Minus 4ac. Okay, now we've got to undo the square, and we've got to take into account they can be positive or minus, so we're going to have to do square root and square root. So that's going to leave us with plus or minus b squared minus 4ac, and so we'll get 2ax plus b is equal to plus or minus the square root of b squared. Who can tell me what's going on? Minus b. Have you seen it yet?
You're getting to the quadratic equation.
That's it. That's exactly what we're doing. So this is where it comes from. So we took the general form and we applied the quadratic, completing the square to the general form, and we end up with the quadratic formula. Da, 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 da. So now you know where it comes from. Now if the solutions exist, we can use this formula to find them, but that same question relents. If we complete the square and we notice that it's above the x-axis, it won't have any solutions. So what can we do? So I'll very quickly do this because we need to get on with the other thing. So what we do is we look at b squared underneath the radical is 4ac, and we call that delta. Delta is the symbol for discriminant. Now we check the discriminant. If delta is positive, then there are two unique solutions. If delta is 0, then there's a double root. In other words, it's a perfect square. And if it's negative, then there are no solutions, no real solutions. We'll make sure we do that. Okay? So for the previous example, I'll just sorry to scroll up out of the way like that. I just want to grab your equation. X squared plus 2x plus 4. X squared plus 2x plus 4. So the discriminant is a equals 1, b equals 2 in the general form, c equals 4. So the discriminant is b squared minus 4ac, which is 2 squared minus 4 times 4. So we've got 4 minus 16. I don't even need the number because I can see that it's a great big negative. Based on that analysis, no solutions. They're introduced to that in polynomials in year 11, I think, but I like to give it to them in stage 5 along with the rest of the quadratic stuff. My feeling is that if students see this, they might not be able to keep up with it, but it's good for them to know where the quadratic formula comes from, and it gives you a chance to show off a bit. But practice it before you do it, because it's a bit trap-worthy, isn't it? There's a fair bit of stuff in there that's trap-worthy. Alright, is there any questions about that? We've brought us to a fair way now. Can I move forward? thoughts, queries, comments? You had enough of me yet? I did tell you your brain would hurt with these sessions. All right. Okay.
Yeah, that was good. I've not actually seen how that equation was derived.
Most don't. Most haven't, mate. You're not alone in that. That's a very common thing, and you'll be able to wow everyone with a couple of integration table thingies, and just do it all practicing first before you before you jump in. All right. All right. So I apologise for that. So we'll do the tube. Okay, I better get my house in order here. I'm gonna now went to, where do I go? Downloads or somewhere. Better open up downloads. There we are. Tutorial on that one. Where did you go? Hey, come on, open. I'll have you open you, please. Okay. There we go. Sorry, I'm just getting lost in my thousands of files that I keep going with. That's the one I want, I think. Okay. Alright, so I gave us a couple of difficult ones just for the fact of being able to have a look at it, I guess, would be helpful. And so it wants us to classify this particular integral as whether it's definite or indefinite. And it's got this twist in it, in that it's got a recurrence formula. Essentially, that's the recurrence formula. If you haven't heard that phrase before, recurrence formulas are mentioned in the syllabus really from stage 5 and stage 6, but then they don't actually serve them up. You don't actually do recurrence formula in the way that we would do them at university, so that's a little bit annoying. But you can look at recurrence formula through the lens of the trig stuff in particular. Yeah, so that's something we can consider. Alright, so what we've got here is, so we've got question 1, and I'll bring that over here because I've pre-done the solutions for this, so I'm being a bit careful about how I unpack it. Alright, so we'll just use our trig substitution. So the trig substitution, that now it gets annoying in maths when this happens, when we use known substitutions. So this would come up in the 4-unit course or the extension 2 course, and this is part of the reason I've done it, because the emphasis has been at this end of the syllabus. But what we would do is we would swap the signs squared. Does anybody have any idea? Have they seen this before, what I'm talking about? I think on the formula sheet that I had before, Where is the formula sheet? It's possible that the formula sheet has got recurrence formula in it. I wouldn't be so lucky, would I, on that one? The HSC one does have it on it, but it doesn't look to be there, so I can't really reference that. Essentially what we can do is substitute our sine squared for the half angle formula. I don't know if you've seen this before. Now what I've tried to do is take the power out of trigonometry by giving you a look at exact values trig. Okay, so the exact values trig means that the heat is taken out of, say, the extension 1 and extension 2 courses, okay, and our subject to some degree. Now, having said that, what's the hard part about trigonometry in the syllabus for stage 6, extension 1 and extension 2? It's these damned trig substitutions that get made seemingly willy-nilly. So that's something that is going to take you a while to come to terms with. But again, I'll give you the exposure so that you can say, all right, maybe this involves a trig substitution. I've got to go to the book and find the trig sub and use it. So one of the solution things here is that we remove the power. Okay, is that we remove the power, and because we're integrating, we can't use the usual techniques when we're integrating. So what we'll do is we'll change the integral from this guy to this one, and we'll insert our substitution. And we're doing it with the theta. So this is quite a tricky one in that sense. But I'm exposing you to tricky ones so that you have a little bit of experience with it. Okay. All right. So if we do any kind of expansion and do these integrals, I'm going to take the half out. I'm just going to take the half out the front. And just have them as separate terms, because then they're not quite as intimidating. And we can actually treat them separately now. So in effect I can put the half out the front of a big bracket if I want to, and integrate the 1 d theta minus the integral of cos 2 m theta d theta. There's nothing wrong with me doing that and keeping the limits the same for both computations. Okay. So what happens here with the first term? This is a simple integration. What do I get as a result of this integration? What do I get as a result of this integration? So all I'm doing is integrating. Now you can see it like that. That's very rude of me to do that, but that's how it can be seen. You may have seen, I might have done that with you actually in Calculus 2, but you weren't all there. So that's like the integral of a number, which is like our integral. The variable's been changed from x to theta. What's the idea there? Well, in here we have a 1. It's just not there. It's like a phantom 1. But when we're integrating, if there's a gap, that's what we see. We see 1. Now, anytime we integrate a number, What that means is that we'll have an indice that's unseen. Why is that so important? Because integration is about manipulating the indices. So what you do is what's another version of 1 with respect to x? So I'm just going to leave a bit more of a gap there. Well, x is there.
X to the power 1.
X to the power 0.
Oh, 0.
So it's 1 times 1, if you like. Okay, 1 times x to the power 0. Now, if we're going to integrate x to the power 0, we're going to find that it's 0 plus 1, 0 plus 1 plus c. Now what we'll get is x to the 1 divided by 1 plus c, and we'll get x plus c. So these gappy ones, this family of gappy ones, are tricky in that what they're doing is, this is the bit that you need to understand. The variable is there, it's just hidden. So our theta variable is there, it's just hidden. It's hidden as 1 theta to the power 0. And when we integrate that, what we're going to get is theta, the result, plus c, but I'm not going to put the plus c in because we've got these numbers. The thing that's questioning whether it's indefinite or definite is whether or not the impact of m does anything. So the result of integrating this term here is we conjure the variable. Now by the change of variable at university, that's quite hard. Okay, at school we wouldn't do that so much, but here we do, so that can be quite complicated. Alright, what about this integral over here? What do we do with the cos 2m integral? Well, we have to do a u substitution. And using Leibniz notation, what's the so you've got to be pretty on your feet changing between differentiation and integration. What's the differentiation of u equals 2m theta with respect to theta?
2m.
That's right, you're just left with 2m, aren't you? So what we want to do is we want to get the theta up by itself and the du by itself, so we're going to cross multiply, and what we'll do is we'll get 1 over 2m du equals d theta, and that's actually the thing we're substituting. There it is up there. So this is very lost. I think I said this to you before. This is very lost on students. They rush over here and say, oh, we're just integrating cos u du. That's all you do. Well, no, that's not quite right, because what about this guy here? The 1 over 2m has to be there as a constant. So this is what the whole game is about. Alright, so when we integrate, so the differential of sine is cos, so the integral of cos will be sine. So we'll have 1 over 2m sine u was 2m theta, and that will be our result for this particular thing. We can put the minus down now, put the brackets back. So this is a bit of a hard one, but I'm journeying it through it with you, so that you have a sense of support here. I'm not going to ambush you with this kind of analysis question on your own. We're going to go back to the more simpler ones for the homework. Alright, so we're still trying to classify this thing and see how it works. So what we've got, I'm going to leave the half out the front, okay, and then I'm going to do the scaffolding. So we're going to bomb everything in that one with pi on 2, and we're going to bomb everything in that one with minus pi on 2. Now I feel that students don't do that. They don't like doing it, but I've found that students who know what they're doing can do it. So maybe it's worth doing. So I'm even going to leave it there as a an emphatic thing to do. So if we put pi on 2 into theta, we'll get pi on 2 minus 1 over 2 m sine 2m pi on 2, and what we see is that they cancel. Okay. Okay, now we can say this if m's not 0, and somewhere I think there m's are real, but for our integration we need m not to be 0. Alright, for the second part we're putting in minus pi on 2 minus 1 over 2m sine 2m minus pi on 2, so they'll cancel, and we'll be left with minus pi m. So we've got pi m up here and minus pi m. Okay, the next thing we've got then is, what do we know of sine m pi? Now, what does m belongs to z mean? So whenever you get an analysis question, you can enter your technology again. I know you love me doing this. Not really. At critical moments, we'll grab the technology again, and we'll literally write m belongs to z, and let's see what Wolfram tells us. Let's see if it helps us out. That's not what I wanted. Sorry, I'm just looking up belongs to in LaTeX, and I'm going to feed Mathematica that one. Oh yeah, in. Let's try that. So this is a bit cheeky. I'm feeding in some LaTeX math to Mathematica, and there you go, it did it. Belongs to Z. So M belongs to Z. Okay. So actually it's still not quite giving me what's the number set for Z? Does anybody know? So we're going to have
the reals.
No, R's are reals. So this is integers. Reals. These are integers. So what this means is that we've got multiples of pi. Now if we go to our exact values trig, what we know is that at pi, what's another name for sine? What have we learned sine means? Right, have I done exact values trig with you guys yet? I covered it briefly in week 1. It's alright, I'll do it again next week. That's fine. So
you covered it briefly in the beginning of this lecture.
No. I'll do that in the coming couple of sessions that we have. Still got know-how sessions to go there. So one of the things that you'll learn is that an association for sine is the y in a triangle. So when we see a triangle that's got y and x, and I'll have to explain this further, we make this association with sine and y. And so when we see sine with an angle in it, this says what is the height of this side of the triangle. That's alright, we'll come to this again. What's the height of this side of the triangle? And so the triangles exist this way in this system, and you can see y's there, this edge, and then what happens is y is getting smaller, and it's getting smaller, and eventually it gets to the point of pi where the size of that triangle y has diminished so much that it's effectively become 0. So for some multiple, some integer multiple of m, for pi we're going to get 0. That product means that that term's being multiplied by 0. So this whole term here leaves us with pi on 2. Okay, now that mechanism that I've just kind of blundered through there with you which I'll cover in more depth when we do exact values trig, is the answer. It's the answer to most of the difficult things that come up in the stage 6 syllabus. So we can do the same thing up here. This time we're looking for an integer multiple of minus pi. Minus pi simply means that instead of going in this direction, I might just change the pen. Instead of going in this direction, we go in this direction. So that means the triangles look like this. And eventually we get to a point at minus pi where we ask what's the height of the y edge of the triangle, and at this point it's 0. So this one also gets to be 0, and so its product with that term means that it's 0 overall. So we're left with minus pi, which is plus. So what that means for our question answering session about whether this thing's definite or indefinite is that having the m an element that was a multiplier of our angle didn't sway us one way or the other with the integral. So this meant that we had a half m pi on 2 plus pi on 2. There we are, adding fractions. So it's pi plus pi on 2. So 2 lots of pi are 2 pi on 2, and then we get a product there. So what will happen is this will cancel and we'll be just left with pi on 2. Now what do we say about integrals that are giving us a number? So it's a definite integral, so we're able to classify that in that particular version. So that's a bit of a harder version. Yeah, I haven't given you that for the homework, so yeah, don't be overly concerned about that one. Alright, are there any questions about it? The process of integration? Hopefully you can see some of the things are common. Okay, and yeah. Alright, so the next part, if you're happy to move on, what I'm going to do is quickly see the formula sheet. And in the formula sheet, we're going to have a look at the average function. So that's the average function in the formula sheet. So we're going to have a look at that for this question. So, oh, you can just write that down if you like. So what we're doing is taking the average to get this depth of the river. No questions about the integration? You happy with that? To the extent that you can be not screaming at me at this point. Alright. Alright, let's get this done so that we can move on. Alright, so this is the question we're looking at. A river is 50 metres wide, and the depth d is at a distance x metres from the shoreline is given thus. Plot the function d and compute the average depth. Well, I'm just going to modify that because I don't like that one. In order for a river to have an average depth, what we'd see is that we wouldn't have, that's an upside down quadratic. We just learned about quadratics. So that's not what I want. So I'm going to change that. I've not noticed that before. And so what I'm going to do is go minus 50x plus x squared and over 10. So that's our depth function. So I've just modified that slightly, if that's okay. And I'm going to change that ratio as well. Don't know why that's in there from there, but we'll do it that way. Alright, so for question 2, we have to invoke this integral. We want the differential because we're finding the average depth. Okay, so from our formula sheet, the formula sheet equation was dash on the top. So we're looking at, which is just like the statistics dash, if you were wondering. Yes, it is the same thing. So what we'll do is we'll do the average depth. Okay, so the average depth. So for this one here, we'll go 1 over the distance between the two is 50 and 0. And we'll integrate between 0 and 50 the depth function dx. Now our river function should look something like this now, where we've got our dip as a positive quadratic that's 50 metres wide, and we're looking for the average depth given that minimum. So the average depth will be somewhere in here. Now in the syllabus for the advanced maths course, and that means it carries over into extension 1, averages are used quite a lot to introduce differential calculus. I much prefer doing that, okay? But the averages confuse students, but they are important because when you do any mechanics like motion, averages explain what's happening in the motion part of the equations. So just hang in there with any average work that you get in your text, but they can be a little bit confronting just to navigate your way. They're basically stage 5 ideas, the average that they use. They don't use this equation, so if I misrepresented that, I apologise. They don't use this. Alright, so we're nearly done, so we can get a wriggle on. Okay, so this is going to be 1 over 50, the integral from 0 to 50 minus 50 plus x squared over 100 dx. And so the integral can be taken, 100 will come out, so it's not actually a quotient. So 50 times 100 is 5,000, so we'll put that out like that, from 0 to 50, and we're just doing them term by term. So this is a dead easy one. It's up and under for each term. Okay, so for up and under we'll get minus 50x will be up and under, so it'll be 1 divided by 1, so it'll be 2 divided by 2, up and under, minus 50x squared on 2, which will become 25, and this one is 3x3 on 3, and then we're going to be doing that between 0 and 50. So we've got our 1 over 5,000 outside. Sorry, that squared becomes, no, that's right. That was not there, mate. You put that in. Just take that off. Yeah, you were doing that in your head, you silly boy. Okay. Alright, so we don't want to do the integration over the factual integration line, sorry. And then finally, we need to do the bombs for 0 and 50. Now for polynomials, and you can only do it for polynomials, if there's only polynomial terms, that won't matter anymore. So you can just shortcut that away. And so we've got 1 over 5,000. Sorry for being late tonight and taking you over time. So this is now going to be 50x squared over 2 plus 50 cubed over 3. And so if we go ahead and do that, we'll end up with sorry, I must be getting tired. I'm making mistakes. How's that? Is that better? So that's 50 to the power 3. 2 lots of 50 to the power 3 over 2 and 3. So there's a little bit of work to be done to get that out now. So I'll tell you what, I'll let you fiddle with it and I'll just give you the right. It's approximately a depth of 4.717 meters. Okay, I'll let you do those couple of lines. So we get the average depth. Alright, so these are effectively just normal integrations. Okay, there's nothing dramatic about these at all. Okay, and that should have a 0 on it too, by the way. I don't know why it doesn't. But that should have a 0 on there, so please amend yours. So these are just basically integrations. I wanted to give you some practice with your integrations. Now look, for the homework sets, the fact of the matter is you can put them into technology to help you check. Now I don't want you to cheat. I know you won't because you're decent people, but I just thought I'd remind you, rather than fumble along on your own, if that's what your situation is, because I'm still developing my understanding of who you are as students in things like integration, because integration is a scary one, isn't it? So I encourage you to use the technology. That's why I gave it to you, so that you can help check. Okay, so check your work, see if you can get those 3 integrations out, and if you do that, I'll be extremely happy. Alright, so hopefully what I've done is I've pushed you to the edge and pulled you back, comfort, 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 pushed you to the edge, pulled you back, comfort, comfort, comfort. And then in the semblance of the evening, you come away feeling, okay, we did some hairy, scary stuff, but at the end of the night, I really feel as though we've got some good work that we understand. Okay, if I'm doing that, I'm doing my job. If I'm not, you need to let me know. Okay, so if I don't hear from you, it's not going to be facetiousness on your part. It's going to be, that is what I will take from it. But if there's something you're saying, Jason, you know, you could change this, let me know, because that's the best way to go forward. Alright guys, I've kept you over right about the time I was late. I'm so embarrassed that I was late, and I do apologise. So thank you for coming.
Jason, with the homework questions, is it just sending in scanned,
Can you
a
put
scan of hand-drawn stuff?
Yeah. Can you put it in the folder, your folder?
Oh, in the folder, that's right.
Yeah,
okay.
Can you just pop it up in your folder?
Yep. I remember now.
If you've got some creative way that you want to put it together, that's fine. If you wanted to just do it and record it and send me the pop the recording up or some link to the recording, that'd be okay. But just the handwritten PDFs like I post is fine. If you want to do it on paper on your desk and scan them and photo them and send them in or put them on your file, that's fine. No problem. Alright, any other questions?
Yeah, I'm sorry, I'd forgotten about the folder.
No, that's alright. Cindy, Trish? Alright, it's time for a long deserved coffee. Alright, or hot chocolate. Alright, good night guys. Thank you for coming. I'll see you next week. Bye bye.